Higher order derivatives, double derivatives, triple derivatives, fourth derivatives.
Okay.
If you were using the definition of the derivative, you would do all that work to find your answer, then take your answer and do all that work again to find the next answer. Or the shortcuts might be nice. Okay? We have our power rule shortcuts. Have you been going through them in your head?
Yeah.
Have you been going e to the x shortcut?
Yeah.
E to the x, 5 to the x shortcut?
Yeah.
5 to the x, natural log 5. Natural log shortcut?
Yeah.
1 over x. Product rule. Keep one the same, derivative of the other one, plus keep the other one the same, derivative of the other one. And then quotient rule. What do you keep the same first in the quotient rule?
Bottom.
The bottom. Keep the bottom the same, derivative of the top, minus keep the top the same, derivative of the bottom, over
Bottom.
the bottom squared. Okay. We're going to be adding more shortcuts. And then we have higher derivatives, which means you just take the derivative again. So you have your first derivatives, now you have your second derivatives, which in the prime notation, you just add another prime. Gets a little annoying when you get to the hundredth derivative. Sometimes they put in brackets, like they put f and then in brackets, they like, instead of writing 100 dashes, they just put a little 100 in there. Say, we want to find the 100th derivative of something. Not very often. But we do use the second derivative a lot. So, with the prime notation, you just do 2 dashes. We can say y double prime. With Leibniz notation, we get creative with what we square. And it kind of works like this. This is a notation for taking the derivative of y. Do d dx of y. Hence, you get the first derivative being dy dx. If you did the d dx of y, does it kind of make sense that just the d gets squared on the top? And technically, on the bottom, the whole thing would be squared. It should have brackets, maybe. But mathematicians got lazy there, and they're like, we don't want to add extra brackets. So technically, the squared on the bottom is not that just the x is squared. It's really the whole dx is squared. But this is where, like, the laziness of mathematicians came through stronger than proper, maybe, notation. So I guess technically maybe it should be d squared x squared, but they just have the dx squared. So, to find the second derivative, all you do is find the first derivative. And then whatever answer you get, do it again. Third derivative. You could write it with 3's in there. Sometimes we have the nth derivative, and then you can write an n in there. Like if you had the 100th derivative, you could write a little 100 up there to help you see that. Okay. So, find f double prime. And we're given f of x. So the first thing you always do when you're looking at a derivative is decide, is this in forms that I have shortcuts for? Okay? The x cubed, definitely can use the power rule. The minus 5 over x, you have a choice. You can either use the quotient rule, not recommended, or you could move that x to the top and make it an x to the minus 1, so you could use your power rule again. Power rule is way less work than the quotient rule, right? Just like bring the number out in front, subtract 1 from the exponent. That's a lot quicker than doing keep the bottom the same, derivative of the top, minus keep the top the same, derivative of the bottom, over the bottom squared. It'll work out to the same answer, but this is easier. So then I can get my first derivative being 3x squared plus 5x to the minus 2. And then we do it again. And you could, in the end, you could simplify, put that x cubed back on the bottom, but you wouldn't need to. There's some very cool things that happen when you do derivatives over and over and over again. Okay? So, one cool thing is with, you see how you went from x cubed, then it went down to x squared, then the next one would go to x. Can you see if you did it again, it would just be 6? And then any more after that would just be 0. So derivatives eventually get rid of something. And okay, I'm going to give you a table of values. Okay. And I'm going to use something, you will probably figure out what I'm using, but I won't tell you. Okay. Now, if you look at, can some of you figure out which equation I picked? You guys are amazing. But if you look at the first differences, okay, it's going up by 3, going up by 5, going up by 7. Those are called first derivative differences, and they're related to the first derivative. If I did second differences, you notice that they're all the same. If the second differences are constant at 2, it would mean that y double prime would have to be 2. If you work backwards, what would y prime be?
3.
If this is the derivative of this, what would have to be here? 2x, right? Because if this is the derivative. And if this is the derivative of y, what would you get?
X squared.
X squared. I don't know, I think that's kind of cool. So if you have a table of values and you start looking at differences, and you all of a sudden you find out, I hit a constant when I got to my x cubed, I could work backwards and know, like when my third differences are constant, then I would know I have an x cubed now. Anyways, some interesting pattern stuff that's connected to things you've done before. These ones are always going up by the same thing. That makes them linear. Find the second derivative if y equals this. So first of all, I would think of this square root of x as x to the half. Okay? Sometimes I would take the time to actually rewrite that to prep myself. I'm getting ready. Is everything else I have a shortcut for? Yes. But I prepped the square root so it was something I was used to. Now, I can bring the half in front, subtract 1 from the exponent. Shortcut for natural log is 1 over x, so this becomes negative 5 over x. And the shortcut for e to the x, is e to the x. Then, could we do the second derivative? And at times, and I'll add it in green here again, I might take the time to do this. Right? Do you see what I did there? I only changed one of them. I changed that x on the bottom to an x to the minus 1 so I wouldn't have to use my quotient rule. No offense to the quotient rule, but the product rule or the power rule is way easier. So by doing that, now I can bring the half out in front again, subtract 1 from the exponent, bring the negative 1, subtract 1 from the exponent, keep the other the same. And if you wanted to, you could put the x to the 3 halves on the bottom and change it to the square root. Textbooks don't like negative exponents. Textbooks sometimes don't like fractional exponents. So you'll see things change back like this. It's not hard. You just need to remember that you can do that. Because on a multiple choice, that might happen.
No.
Okay. do you see you have a product rule? Even if you would distribute the e to the x, you would have product rule. So how do we do our product rule? If I take out my highlighter, just to, as like help us visualize it, we have our first function, we have our second function, and we're multiplying them. So we keep our first one the same, multiply by the derivative of the green one. Then we keep the green one the same, and multiply by the derivative of the yellow one, which keeps it the same. Or doesn't. It's new. It's the new same function that it was before because you did the derivative. And then you're going to have to do the second derivative of this. If you would do the second derivative the way the equation is right now, do you see that the second derivative has a product rule followed by another product rule?
Yeah.
Perfectly fine if you do that. However, if we take some time to manipulate, like I see, I can factor out the e to the x. Why might that be nice? Well, now I only have one product rule with, take out my highlighter, this is your first, oh, it's green. There we go. This is your second one, this is your first one. So then how do we do it? We got to go to y cubed. So had we done double product rules, can you see how big that would look? And then your triple product rules, like they're getting bigger. So how do we do the product rule? Well, I'm going to take out my highlighter. I keep the first one the same, then I do the derivative of the second one. Then I keep the second one the same, and I do the derivative of the first one, which is an e to the x again. And again, for finding y prime, what could we do? We could do a double product rule. But can you see you can factor out that e to the x again? Things are getting bigger and bigger every time. And we would keep the first one the same. Keep the first one the same. Derivative of the second one. Plus, keep the second one the same. Derivative of the first one. And if we factored it out, I'm sorry, I'm playing around with this. This looks like fun. I am going to write the only reason I did that is I noticed this one had a 1 plus x cubed, this one had a 1 plus x cubed, so I made this one have a 1 plus x cubed. And then I wondered, is there a way that I could find a shortcut to do one more? No, we shouldn't spend time on this, finding a shortcut, and then quickly be able to find y to the 7 really with it. I think there's a shortcut to be had there. I think we could figure something, but we won't. And I see the optimism and the excitement brewing from you guys. Oh, let's do more math, yay. Okay. But you'll get some questions like that sometimes, that the patterns occur. How did it, like it went from 3x squared to 6x squared to 9x squared. Would the next one have a 12x squared? I don't know. Then it went from no x's to 6x's to 18x's. Oh. Anyways, that kind of stuff is fun for me.